Well, hello everybody. It's the bonus quiz for 5.6, and if you have been following along on the PIMA plan, that is if you've gone through Math 82 and Math 92 and worked your way up to Math 122, this particular section represents a new station. It's new mathematics. That is, you've never had in your past this idea that you can actually factor the sum of two cubes like this into this binomial and this trinomial. And you can factor the difference of two cubes into this binomial times this trinomial. Notice they're almost exactly alike, except for this sign, that differs, and this sign. And that was a way when I was in school, they had us memorize this. And you fortunately can bring in the formula into the exams or on your quizzes. So really what this comes down to is being able to recognize that you have the difference of two cubes and then being able to run the right formula. And really, it becomes a glorified substitution problem. Now, remember, I said this course is all about substitution. And here we are again. Now, when I first look at this problem, I don't see straight away that I have the difference of two cubes. That's what they're going to do. They're going to camouflage that fact in a lot of different ways. And you're going to have to do some massaging. And, I see that the first term is certainly a cube. If I rewrite 27, though, factor it, you realize that 27 is equal to 3 times 3 times 3. It's a perfect cube. And now I do in fact have the difference of two cubes. And I can run this formula right here. Wherever x appears over here, it's going to really be my s. And for y, this is the y spot, this is the x spot. Wherever y appears over here, I'm going to have 3. And it becomes just a glorified double substitution problem. What I would do is I would go ahead and create the binomial and the trinomial, and go ahead and copy the signs. I think that's where people fall down, is they get a little bit twisted. Put those signs in there, then you're not going to worry about negatives and positives. You just simply follow the formula. X is my s, y is my 3. I'm going to have s minus 3 here. S minus 3. And then the next term, the first term of the trinomial, well, what's in the x spot is s, and we square it. And then the next one is you multiply out whatever in the x and the y spot. Multiply them together, and you get S3 or 3s, as we prefer to say it. And then the last term, it says whatever in the y spot, in this case 3, square it. 3 squared is 9. It's really just glorified substitution. Here's the key idea though. It just so happens you have a binomial here and a trinomial. And if we were to multiply it out, we'd have 3 arrows running from that s, and we'd have 3 arrows running from that negative 3. We get 6 terms in all. And it turns out that most of those terms would cancel each other out, and we'd be left with just 2, s cubed minus 3 cubed. You hear a lot about multitasking in our culture. Well, math is really about multi-directions. That is, being able to go from left to right and from right to left. In 5.6, we're going to go from left to right. In earlier chapters, we had this, and we went from right to left. So I've already typed the answer in here. We're good to go to the next problem, where the complexity of this increases dramatically. Do you see straight away the difference of two cubes here? I certainly don't. And you're going to have to play around with these. To evoke the formula, you're going to have to see if the formula applies. And this is obviously well camouflaged. Now, I took this number here. My first move would be to see if there's anything in common I could factor out from these two terms. This has C's and this doesn't. This has D's and this doesn't. The question is, do they have any factors, number factors in common? So I took 343, and the first number that went into it was 7, and it went into it 49 times. And then, of course, 49 consists of 7 times 7. So the prime factorization of 343 is 7 cubed. Remember, you take the leaves of the tree. It's an upside down tree. And you can do the same thing for 64. It consists of all 2's. In other words, this is an incredibly even number. And this is an incredibly odd number, and they don't have any factors in common. So there's nothing you can pull out from either one of these, and really we're stuck. If we're going to factor this, it's either going to be the difference of 2 cubes or it's not going to factor at all. So can we make a cube out of this? Well, we know that 343 is a perfect cube, so that much is clear. Well, what about this c to the 6th? Now that's a little more difficult. C to the 6th can be rewritten as a perfect cube like this. I'm going to evoke the laws of exponents. powers to powers you multiply. So this is in fact c to the sixth. But notice I've written it as a perfect cube. In other words, c squared right here works. When you multiply these out, you get c to the sixth. So the first term could be written as a perfect cube. And it's the same game here. Write 2 to the 6th as a perfect cube. And use the laws of exponents. 2 squared, which is 4, to the third power. Notice you get 2 to the 6th back because you multiply these two out. So 4 to the cubed is the same as 64. And then, of course, d is the same as c. We can rewrite it as d squared. And so now I have the difference, the subtraction of 2 cubes. And I am free to run this formula right here, where my x is going to be this conglomeration, 7c squared. Wherever x appears, I'm going to replace it with 7c squared. My y, I'm going to replace it with 4d squared. And I'm going to have to be careful here doing these multiplications, but really that's all there is to this. A very complicated substitution problem. I wanted to solve this a slightly different way. I think this is pretty cool. This is an old math teacher's trick. I want to use the multiple choice answers here. Which ones of these will multiply out to this? And one of the things I noticed right away here, look, when I do these multiplications, I'm going to have to get a c to the sixth, because I have a c to the sixth here. And the biggest c I have over here is c squared. So it doesn't matter which one you multiply against. C squared times c squared in this case is going to be c to the fourth. C squared times c squared in this case is going to be c to the fourth. I never get c to the sixth in any of these multiplications. There's going to be 6 of them. I'm never going to get c to the sixth. So it can't be answer A. It can't be. And it's the same thing here. Here I have c to the cubed. And I have c squared here and c squared here. Well, it doesn't matter which one you multiply against. You get c cubed times c squared is c to the fifth. I don't get back c to the sixth. I don't get back the original, and so it can't be b. And it's the same game here. I have c squared here, and the biggest I'm going to get is c to the fourth. And so it can't be c. Notice here, when I do this multiplication, I do in fact get c to the sixth. And this is the only answer it could possibly be. And so the answer here is D. And I did that by just checking for the first term. That when I multiplied out here times here, I have to get 343 c to the sixth. And this is the only one that does that. And that's a nice little hack there that really makes this problem break open a lot faster. Okay, I hope that helps. Good luck with this section.